Bueno, gracias por participar. Hay un par que conozco acá, así que bienvenidos a todos. Bueno, voy a presentar a la disertante del día de hoy, Marie Plaisir. Encantada de tenerte acá, por supuesto. Marie está en estos momentos en Córdoba, debido a un proyecto que tenemos en conjunto con UTN para el estudio de prefactibilidad de hidrógeno verde en la provincia. Así que aprovechando que ella estaba por nuestros lugares, la invitamos a que nos comparta algo de sus conocimientos en este tema. Así que, Marie, bueno, la temática es el rol del hidrógeno en el futuro, así que bienvenida y muchas gracias.
Thank you, Carla. Yes, I would just start into the presentation, introducing myself just for a second and start sharing my screen. Is it working? Perfect. All right. So I will try to give you a short 40 minutes introduction into the topic of the future role of green hydrogen. My name is Marie Plaisir, and I am the project leader of the project that Carla just announced from the Fraunhofer IEE. I'm working at the Fraunhofer Institute for Energy Economics and Energy System Technology since 2018. We are doing research mainly in the topic of system transformation towards renewable-based systems. Our service portfolio deals with current and future challenges that energy industry and energy system technology is going to face or is already facing. We are 430 employees at the Institute, including all the students that are working with us, and our annual budget is close to 30 million per year. My background is in industrial engineering, and I have my master's degree in renewable energies and energy efficiency. And since 2018, I'm working at the Institute in those Power-to-X and green hydrogen related topics. Our Institute is not only dealing with hydrogen, but with the whole energy system and its transition. I have colleagues who are into grid planning and grid operation. I have colleagues that are into system stability and grid integration. The division where I come from is energy process engineering and energy storage, thermal energy technology, energy informatics, energy economics and system design, which is also something I'm going to present to you in a second, and energy meteorology and geographic information systems. Just to give you a short overview of our institute. Okay, the future role of hydrogen, the future role of green hydrogen. Hydrogen offers a wide range of potential applications. On the one side, today, many fossil-based fuels are used for energy supply, but also as raw material in many industries. So hydrogen can be a substitute for fossil-based products as a raw material, as feedstock for processes, but it could also be an energy carrier. The long-term goals are defined in the Paris Climate Agreement, and therefore it is important. Hydrogen is an important element of the global energy transition to achieve those goals that are written down in the Paris Climate Agreement. As I said, hydrogen offers a wide range of applications, especially in those sectors that are difficult to electrify, including but not limited to the replacement of current fossil hydrogen consumption, steel production, concrete industry, chemical industry, and fertilizer industry. At the moment, there is a global production of around 120 million tons of hydrogen per year. About 67% of it is pure hydrogen, and the rest is a mixture with other gases. It is mainly needed for oil refineries today, at least at the global scale. Half of the global demand of hydrogen goes into refineries. Ammonia production is the second most important thing, and the rest is pretty unimportant from this global point of view. In the European Union, there is a production of around 10,000 million tons per year. And in Europe, ammonia is the most relevant usage of this hydrogen. At the moment, only 2% of the current hydrogen production comes from renewable energies, which we call green hydrogen. And the rest is coming from natural gas, from coal, from oil, and the emissions which are coming from fossil hydrogen is around 2% of the global emissions. That's almost as much as the whole aviation sector is emitting. The current global demand is growing. On the left-hand side, we can see how it grew between 1975 until 2018 and what it is used for. And on the right-hand side, there is a graph showing the perspective of future demands of hydrogen. Today, as I said, it is mainly supplied from fossil fuels, and in the future, we hope so, at least, it will be green hydrogen. The role of hydrogen in an energy system is the next slide that I want to present you, and I brought an example from Germany. Here, give me a second to use the laser pointer, then I can show it to you on the slide. This is the expected final energy demand of Germany if there is a net zero system in place. We are expecting to have an energy demand in 2050, hopefully already 2045, of around 2,000 terawatt hours per year. And on the left-hand side, this is mainly heat needs. No, this is the energy that comes from the biomass is the green part, and other sources is the gray one, but most of them are going into the heating sector. And on the right-hand side, this is the electricity-based electricity demand that we will have. But for Germany, it is definitely not possible to produce all that what is needed, which is the whole amount here in our country, because we do not have enough area we do not have the good resources. So resources and demand are not located at the same spot. And in the future, as we are today as well, today we import fossil fuels, but also in the future, we will have to import energy. And this is just an example for hydrogen and power to liquid, which is one of the power to X processes that I will go into. This is the amount that we need to be supplied from anywhere in the world, and this will be hydrogen or hydrogen-based products that we have to import. A short introduction into the colors of hydrogen. At the moment, we are dealing with gray hydrogen. This is what the most of the hydrogen production today is coming from. Gray hydrogen is natural gas that is transformed into hydrogen via natural gas steam reforming. The CH4, the methane, is split into CO2 and hydrogen, and the CO2 is emitted. So the greenhouse gas pollution is high and the sustainability is pretty limited. Green hydrogen is the production of hydrogen coming from renewable sources like wind and solar and hydropower, and it is produced via electrolysis, water splitting electrolysis. It is almost carbon free. There is always carbon emissions in the production of the steel for the wind farm, for example, but it is definitely one of the production methods that lead to high sustainability and to none or low, in some cases also negative, greenhouse gas pollution. The projects today are mostly about green hydrogen, but maybe you also heard about blue hydrogen, which is gray hydrogen, meaning reforming natural gas, but capturing the CO2 that is nowadays emitted. This CO2 can be captured and stored, for example, in depleted gas fields, and this has lower emissions than the gray hydrogen, but it will never be zero. And the methane leakage from the pipelines is also something, because of the higher impact regarding greenhouse gas emissions of methane compared to CO2, this is not sustainable. There are even more hydrogen colors. Turkey's hydrogen is hydrogen that comes from methane pyrolysis. This does not require hydrogen or a CO2 infrastructure because the carbon is solid and not gaseous. But the efficiency of this process is worse than green hydrogen, and we again have the same problem like with the blue hydrogen, that there is always some kind of methane leakage that cannot be avoided. Regarding green projects, there is a pretty huge power to X pipeline worldwide. There are many projects announced that want to install gigawatt scale production of green hydrogen coming from wind or solar resources. There are also projects announced that are into hydrogen or hydrogen derivative transport, infrastructure, and large-scale industrial usage. The amount of money that is announced is huge, and that these $500 billion US, which have been published by Hydrogen Insights, that is a figure that is already, because this whole sector is really flexible and really fast. We should update this slide every day because there are announcements every day. Regarding the European targets, Europe announced that they want to install 6 gigawatts until 2024. leading to the production of 1 million tons of hydrogen per year. And in 2030, they want to have 40 gigawatt of electrolyzer capacity installed, which is really, really ambitious due to the fact that those large-scale projects are not yet implemented. There are many projects already in operation, but they have a completely different scale. The next problem that we will face, at least for the next 5 years, is that there is a shortage of supply regarding electrolyzers. If we want to install these huge amounts of electrolyzers, we also need manufacturers for that, and the supply chain still needs to be developed. In 2021, this is published by Sunfire, and we know that the figures are not totally right regarding this side, but it is what it really presents in a precise way is that the annual manufacturing capacity nowadays is less than 2 gigawatt worldwide, and all of these companies announced the capacity ramp up until 2025. And as I said, the figures are not totally correct because from Siemens, for example, we know that they want to go for 2.5 gigawatts. So this figure is not totally correct, but it just presents the way that the electrolyzer manufacturer are preparing for this ramp up of green hydrogen technology. If we analyze the announced projects and their scales, there is a shortage in electrolyzer supply until at least 2024, probably longer, of more than 3 gigawatts per year, which is causing at the moment high prices for electrolysis technology on the market because the demand is a lot higher than than can be offered on the market. The next 3 slides are short introductions into projects that are already in operation. In Germany, we have this Energiepark Mainz project, where the hydrogen is produced from wind energy via a PEM electrolyzer. The electrolyzer has a capacity of 6 megawatts and is connected to 8 megawatts of wind. There is a ton of hydrogen storage installed, and they are testing and combining different operating modes and also different applications. So there is this storage capacity, but they also feed some of the hydrogen into the local gas grid. And they have a trailer filling station to, for example, supply hydrogen refueling stations. In Werlte, there is a power to gas project in place. So in Mainz, the previous slide, that is pure hydrogen, which is produced. This plant in Werlte is producing synthetic natural gas, meaning a direct substitute of fossil natural gas. It is producing the green hydrogen, and in a second step, using CO2 as a second feedstock, as a second raw material coming from biogas in a Sabatier reactor for methanation, leading to synthetic natural gas. Probably the largest electrolyzer which is in operation, at least using the PEM technology, is a project that is called REFINE, and it is a 10 megawatts PEM electrolyzer that is located directly next to a refinery. The aim is to deliver green hydrogen for cracking processes in the refinery, and this is just the first stage of implementation. They plan to expand this project up to 100 megawatts. To give you an overview of what an electrolyzer is looking like and what are the components, the heart of an electrolyzer is definitely the stack, or the stacks if it is a larger plant. But there is also water treatment required. There needs to be a water cooling system, a circuit somehow. The hydrogen that is produced has to be purified for further usage. The hydrogen has to be stored in buffer tanks before it can be transported or fed into a grid or whatever. Compressors are needed because I'm going to present you the pressure levels on the next slide, but many of the electrolyzers do not have a certain pressure amount that would be applicable for storage needs or transport needs. There always has to be a power supply, like transformer stations and rectifiers, and a lot of balance of plants like control panels or the control room. It is complex, but it is not rocket science. To give you an idea of the footprint, if we are talking about 100 megawatts project, then ITM was publishing a footprint need of 16 to 25 square meters per megawatt installed. These are the three most relevant electrolyzer technologies. There is the alkaline electrolysis, AEL. There is the PEM, which is polymer electrolyte membrane technology. And there is solid oxide electrolysis, which is a high temperature approach. The alkaline technology is a mature technology. It was installed already in early years, the 1950s. There have been electrolyzers in operation that already had been fed by hydropower electricity, leading to ammonia production, which is exactly what we are discussing at the moment worldwide. But that was already in place years ago. So the alkaline technology is the most developed one. It is pretty easy to manufacture. That's why future large system costs will be the cheapest of those three technologies, but it has a huge disadvantage due to the fact that most of the electrolyzers in the future, if they want to produce green hydrogen, have to handle fluctuating electricity production. The flexibility of an alkaline system is pretty limited. That is the biggest advantage of the PEM electrolysis, which is also already developed, but there is still a longer way to go regarding scaling and regarding cost reduction. It has a compact and simple system design and really high flexibility, meaning that ramp-up times are short, or the response to changing input parameters of electricity supply is really, really good. But it requires some special materials that are not providable in those amounts that would be necessary to put PEM electrolyzers to all the projects that are announced. Or on the other hand, the other conclusion we could make from this point is there is also regarding PEM technology technological advancement necessary, leading to lower material demands for production. The high temperature electrolyzer is working at 700 to 850 degrees, which leads to a significantly lower electricity consumption per kilogram of hydrogen produced, meaning a higher efficiency regarding electricity consumption, but it definitely needs a heat source to provide those 700 to 850 degrees. This technology is not developed completely until now because it is degrading really fast. So the degradation is a problem, leading to lower lifetime of the system. And as I said, a heat source is required. Regarding the size of and the cost reduction, the learning curves is the one side, and the other one is economies of scale. This slide is dealing with economies of scale, meaning if we install 2 megawatts of electrolyzer, this will have a certain specific cost because there is one transformer, one rectifier feeding one stack. And if we are going to 20 megawatts, so 10 times the size, then the rectifiers or the transformers, the balance of plant can be shared by the whole project, by the whole plant, and that is leading to a really significant cost reduction regarding specific costs. So from 2 to 20 megawatts, the cost reduction is 50%. And if we then scale another 5 times from 20 to 100 megawatts, then another 30% of cost reduction is expected. If we are then going for a gigawatt project, the cost reduction is only 10%, but there still is economies of scale in those ranges, which always lets us, from the perspective of developing first projects in the world, we are always aiming for projects for first large-scale industrial scale projects, not aiming for too high figures because there are many projects that announce gigawatts, but this is a size of a project which we think is realistic and also handleable, as there are no systems operating until now which are bigger than 10 mega. Now my screen is frozen, but can you see the last slide? The cost reduction, or did something change?
I mean, your presentation.
The presentation. Okay. I would just try to fix that. Just try again. No, PowerPoint does not want to react anymore.
¿Tienen alguna pregunta hasta ahora para hacer, aunque sea en español, y lo vamos traduciendo? Mientras recuperamos el PowerPoint. ¿No? Bueno.
No. Perfect. Okay, so I will skip all the slides that we already had. This one was the next one I wanted to go for. As electrolysis is splitting water with green electricity leading to green hydrogen production, there is always water supply needed. It is not only for splitting the water to convert it into hydrogen, but also for cooling reasons and process water as well. What is really important to us regarding sustainability of green hydrogen projects is that the projects need to be designed without conflicts of use with agricultural or drinking water supply, making sure that it does not cause any negative impact on water supply for the people, for food, for drinking reasons. To produce 1 kilogram of hydrogen, that is shown in those few formulas at the bottom, there is a theoretical amount of 9 liters of water. The industrial electrolyzers need around 10 to 12 liters of deionized water per kilogram, but then there comes the additional demand for cooling reasons and for process waters. What is hydrogen able to provide in a future energy system? If we are coming from the green electricity here on the left, then the first step always is making hydrogen out of it, only from the hydrogen perspective. Hydrogen can also come from industrial processes as a byproduct, or it can come from biomass. And of course, it can be imported and fed into the system. Hydrogen is able to supply storage, seasonal storage, long-term storage provisions. It can be stored in huge salt caverns, a huge energy content that can be stored there, and that is one of the future roles of hydrogen in the system. Combining the hydrogen with CO2 and doing a methanation can directly substitute natural gas, which is existent at the moment. And pretty many studies are also analyzing blending, which means mixing the natural gas with the green hydrogen in the gas grid. The green hydrogen can be re-electrified, power to X to power, via the storage process value chain. It can also be used for buildings in terms of heating them. It can be an industry feedstock as a raw material, but it can also deliver high temperature heat to the industry. And then there are many applications in the transport sector, like aviation, heavy duty transport, fuel cell electric vehicles, fuel cell trains, and shipping. Not all of them are really the most efficient, but it is possible. And how can we feed the green hydrogen into the aviation? That can be done, for example, by the process of renewable power, producing hydrogen from electrolysis, and then synthesizing it in a Fischer-Tropsch process. This is leading, if the green hydrogen together with CO2 is synthesized in this Fischer-Tropsch reactor, this leads to a product which is similar to raw oil, which then can be split into all the fractions that raw oil can be split into as well, into diesel, into gasoline, into kerosene. This is, from the point of view of today, the only pathway to fuel airplanes in the future, because there are already announcements of Airbus, for example, who are studying short to medium distance airplanes, or they are studying if they can fuel them with hydrogen in the future. But for long distance aviation, there is no technology known until now that can substitute kerosene in the aviation sector. Regarding mobility in cars, there are definitely more efficient alternatives for the future than processing the hydrogen with a certain efficiency from the renewables. There is another loss of energy in this next step, and then again burning it, which is also not efficient in a common diesel motor, for example, diesel engine that leads to a lot lower efficiencies than fueling cars in the future with electricity. As I already said, another pathway is the methanation, leading to methane as a direct substitute for natural gas, which could also be needed in the future for industry needs. One of the two, at the moment, most intensively discussed pathways is the methanol synthesis. Methanol is one of the most used raw materials for the chemical industry, and that has to be replaced somehow in the future because they need the methanol for feedstock reasons and not for energy supply reasons. And from the methanol, there are certain other routes possible, refining it and converting it again into all those fossil fuels, or making via the methanol to olefins route products like ethylene or propylene out of the methanol. And the probably most discussed and most appreciated process nowadays is ammonia production, because all these processes that I mentioned before, they need CO2 as a feedstock for producing the final products. Ammonia, as it is NH3, needs a nitrogen source instead of CO2, and nitrogen is around about 80% of the air. So it is a lot easier to get high concentrated nitrogen to synthesize the ammonia with the green hydrogen. And ammonia nowadays is produced mainly from natural gas, but there will always be the need of ammonia in the future because it is the main feedstock for all the fertilizer production in the world. As I'm talking about green ammonia, just a short picture. Again, the green electricity production, the water treatment, and the electrolysis here. Next step is the ammonia synthesis, and then in the end, there is carbon neutral ammonia. As I said, that it is pretty ambitious or difficult to synthesize those carbon-based derivatives of green hydrogen. There is always the question, where does the CO2 come from if we are going for methanol or kerosene or methane or diesel? That is always a question that is present, and there are several different potential sources where it can come from. CO2 can come from combustion processes for electricity generation, from coal, from natural gas, from fuel oil, or from biomass. But as we are aiming for an energy transition, those processes will probably not be relevant for the future energy system. So it does not make sense to use these CO2 sources to which can lead to so-called lock-in effects. Because if we base our methanol production, for example, on fossil fueled processes, then there is the need to produce green methanol from fossil combustion processes. The chemical industry has CO2 emissions that which cannot be avoided in the future, because they come from processes. They come from that is so-called non-avoidable CO2 emissions in the future. So if we have them, we can either, in the future, we can either capture it and store it somewhere underground, or we can try to keep it in a closed cycle, using it and then reusing it for ammonia, coming from ammonia production nowadays, for example, but in the future also from ethylene. Cement is one of those industrial processes where the CO2 emissions cannot be avoided in the future, where we have this chance, and CO2 from the atmosphere can be processed via so-called direct air capture, DAC, but as the share of CO2 in the total air is pretty limited, there is a lot of energy required for filtering the CO2 from the air. But that would be the closest, a real closed cycle, emitting it while burning the methanol and then capturing it from the air again afterwards. This is my final slide. What are then now the applications where it makes sense to use green hydrogen in the future from the energy system perspective? It definitely makes sense to use the gray hydrogen, the green hydrogen where the gray hydrogen is used today. For example, the hydrogen which nowadays comes from natural gas reformers to feed refineries, ammonia or methanol production. The direct use of hydrogen in the industry is also very relevant, because there are many processes in the industry that require high temperature heat and that will probably not be possible in an efficient way based on electricity in the future. Burning hydrogen in power plants is another option to stabilize the electricity system in the future, because there will be times when solar and wind power generation is not sufficient to meet the demands of electricity in those times, and then hydrogen can have the role of generating electricity, which initially came from green electricity, to stabilize the grid. As well as for district heating systems, but the heat pump is a more efficient technology. So if heat pumps for every reason should not be applicable to some industrial process or to a district heating grid, then hydrogen can be an alternative. As I said, there are unavoidable consumptions of hydrocarbons in the future. That was my aviation example. At the moment, we do not know technology that could substitute carbon-based fuel in the future. And the same applies for substitution of fossil raw materials for the chemical industry. They simply need the carbon atom for processing their products. The direct use of hydrogen in the transport sector is not as not as straightforward as the other four, because there is a competition with electric drives, with electric heavy-duty vehicles in the future. But there might be applications for trains where electricity lines for train supply cannot be built. It can make sense to use hydrogen in that sector. And the direct use of hydrogen for low temperature heat is something, as I said, which we see pretty critical, because there is the more efficient alternative of using heat pumps, which can be supplied by air, ambient air heat, or by ground sources to feed the heat pumps. This was my presentation for today. Thank you very much for your attention, and I'm looking forward to questions if you have some.
Bueno, gracias Marí, la presentación muy buena. Espero que a todos les haya gustado como a mí. ¿Alguno tendrá alguna pregunta para hacerle en este momento? ¿No? No, bueno, estuvo súper claro entonces. Sí. Bueno, vamos a subir la grabación como siempre a YouTube de la SIUD, de la Secretaría de Relaciones Internacionales de la Facultad Regional Córdoba. Así que si lo buscan en el canal de YouTube, lo van a encontrar la semana que viene colgado. ¿Sí?
Bueno, muchas gracias. Les quería comentar, yo soy estudiante de la UTN, de la Facultad Regional de Resistencia.
Gracias,
Chaco.
Adiós.
Y, hola, ¿me
no hay
escuchan?
preguntas, sí. ¿Ah, sí? No lo escucho.
Sí.
Oh, sorry. Hola, ¿alguien preguntaba algo?
Sí, no sé si ahora me están escuchando.
Ahora sí, perdón.
Bueno, les comentaba que soy estudiante de la UTN, de la Facultad Regional de Resistencia, y bueno, un profesor con el que estamos cursando una materia de energías renovables nos recomendó la charla. Y
¿Walter?
Sí, Walter Morales. Y me pareció súper interesante, y quisiera hacer la pregunta acerca de qué proyecto están trabajando en Córdoba con el hidrógeno.
What kind of project are we doing together now? Can you explain that? Yeah.
Thank you for that question. At the moment, we are carrying out a pre-feasibility study on the potential for green hydrogen in the future. We are looking into the renewable resources that are necessary to produce the green hydrogen, and we are also looking in potential demands. As agriculture here in Cordoba has a strong impact, we are focusing on the ammonia that is the basis for all the fertilizers that are needed. And that is what we already found out. As there is no ammonia production here in the province, maybe it makes sense to substitute the ammonia imports. But in total, we want to present a final report in February to the ministries and to our customer, including information on how to succeed with the implementation on Power to X as part of energy transition. What is needed, what is required. There should be some kind of policy, there should be regulation, there should be also criteria how to deal with those projects in terms of sustainability, for example, of water treatment. There are so many aspects that we are currently discussing and analyzing regarding Cordoba, and that is at the moment our first project that we are jointly doing together, UTN and Fraunhofer IEE.
Thank you so much. Thank you. Yes.
Sí, les vamos a pasar ahí en un segundo, si estás, Anita, el link al canal de YouTube.
Yes, I'm looking the link. So, perdón, en español. Estoy buscándolo.
Tomás, te veo con ganas de preguntar.
En realidad me perdí la primera parte de la
¿Estás
presentación.
muteado? ¿O no? ¿O soy yo?
No, sos vos, Carlos.
Ahí estoy.
Sí, en inglés. ¿Ahí me escuchan?
Sí.
Ahí. Me perdí. I lost the first part of the presentation, actually. But I was thinking while you were talking, which is the time frame for this new technology to happen? I know, we hear all the time about this, and it looks to be a pretty big thing. But just I was wondering, you're more experienced than me.
Could you mute?
Por eso estoy con el sonido apagado, porque nos estamos solapando.
Yes, this is a good question, because at the moment, from energy transition and greenhouse gas effect perspective, it does not yet make sense to use hydrogen in several applications, because the more efficient technologies are the electric ones. So we should start to implement wind and PV for supplying our electricity demands. But as the time that is left for this zero emission system, which many countries committed to, and to have such a system in 2050, we need to start this now. And that is what we see. At the beginning, I had a few slides on how the ramp up is expected to be, where the demands will be, and that the huge potentials in terms of renewable resources as well as area. There is still area needed for the installation of all those technologies, that they are not where the centers of the demand is. So Europe, for example, announced huge amounts of money for implementing international projects to supply Europe with green energy. And that is, we need to start that now, and there are definitely already today applications for green hydrogen and derivatives where it makes sense to substitute it, for example, in the ammonia, because we can really avoid emissions coming from natural gas if we are using the green hydrogen with nitrogen from the air. There is no carbon atom involved. That is a first step that is necessary, or that is reliable, that makes sense. But yeah, for Argentina, for example, I would say it is from the energy transition perspective and from our green point of view, it would make sense to install a lot more wind and PV capacities for electricity production before going into producing too much power to X products for the export, for example.
Thank you for the answer, and surely I'll check the first part of the presentation later. Thank you.
Perfect.
Bueno, ¿alguna otra pregunta? ¿No? Bueno, muchas gracias por participar. Ahí vamos a colgar el video la próxima semana. Y esperamos que se sigan sumando las próximas actividades que vamos a tener durante el año que viene. Gracias, buen fin de semana. Adiós. Chau, chau.
Bueno, gracias.
Adiós,
Gracias.
gracias. Luego.